In our last lecture, we focused on inference on a single population, in particular the mean of the population. With this lecture, let's extend beyond a single population to more than one population, and I'm going to call this a comparative inference lecture. As I noted with the last lecture, we did basic inference. In that lecture, we established the language and statistical concepts with a focus on one variable. We talked about sample statistics, sampling distribution, hypothesis testing, etc. Now, the real fun comes in when we're looking across variables to formally test if they're different, if they're related. Ultimately, indeed, building predictive models is all about that, using other information to come up with predictions on another variable. When we're comparing variables, let's consider the different combinations of what these variables might be. Remember, there are variables that take on values, which we can call numeric and categorical, or sometimes referred to as nominal. For example, if we look at a numeric here from the British marketing example, age, against versus a categorical, cola, we see the visualization of a box plot. What are the techniques in this situation? Well, we can ask, is there a difference between the means between cola and non-cola drinkers in terms of age? So we can do mean comparison testing with a t-test. If we have two variables, we can expand to 3 or more variables with something called ANOVA. We can actually use regression to summarize this situation. And later on, we could talk about regression trees to exploit the information of the categorical for prediction of the numeric. Numeric versus numeric. Here's a data set that we're going to look at a lot in the regression section. Home prices in thousands against square footage in thousands. We see a positive relationship. So what are the techniques we can use for numeric versus numeric? Well, we can talk about correlation estimates and testing. We could talk about, of course, standard regression. And again, we could talk about the use of regression trees. What about looking at a categorical against a numeric? Here I'm plotting if the individual is a friends watcher or not against age. Here we're using age to predict in the end the likelihood that they are a friends watcher or not. This situation is often called a classification situation, and we use techniques like logistic regression, and there's something called, as opposed to regression trees, classification trees. A categorical versus a categorical, we've seen that with a mosaic plot. Cola drinking versus friends watching. Beyond the visualization, we could do things like contingency table testing, again, logistic regression and classification trees. Let's start out with numeric versus categorical, and let's consider a new example. This is a Sports Illustrated article that is speaking about a book that was written. The article is titled "One Reason NBA Superstars Don't Get Fouls Called on Them Because of the Home Crowd." And the writer of this article quotes some statistics from a book, and you can see the name of the book. I'm not going to read through all of it, but let me read a bit. I want to look at one specific aspect, why it means NBA superstars get more fouls called in their favor. Even more to the point, LeBron draws fouls more often at home than on the road. At home, he averages 9.8 free throw attempts per game and 7.6 on the road. So this is the argument that by getting more free throw attempts at home, the home crowd is influencing the referee to favor the superstar home player, 9.8 versus 7.6. Now, right off the bat, because the numbers are different, the sports writer is basically saying, case rested. but we should know that variability occurs. Is 9.8 versus 7.6 significant? Well, let's take a look at LeBron.
I've looked at several seasons since that Sports Illustrated article, and the conclusions are no different. Here's just one year. This is the year of 15-16 when LeBron played for Cleveland in the championship year. Now, what the article fails to consider are the number of minutes played, because you might have games where he plays more and thus has more free throw attempts, or less and less free throw attempts. So to equalize the playing field, I'm going to look at free throw attempts, minutes, and then divide to get the number of free throw attempts attempted per minute. That will really give a fair analysis. I have that in the third column, and then in the next column I have a symbol indicating if the game is away with this @ sign, or H for home. Let's start out with a visualization. We can see here a box plot comparing the away versus the home games. And it doesn't seem like there's any significant difference between the different locations. We already have sort of a conclusion that we're now going to formally test. Formally speaking, we're testing the null hypothesis that the two population means are equal versus the alternative they're not equal. Here, we're testing the mean of away equals mean of home versus they're not equal. Another way to state the hypothesis is that the difference between the two means equals 0 versus the difference is not equal to 0.
So we have two populations, population 1 and population 2, and we have mean 1 and mean 2, mu1 and mu2, but these populations could also have different variances, so we have to be cognizant of that fact. I'll call these variance parameters sigma 1 squared and sigma 2 squared. So why do I mention the variances when we're testing means? Well, it turns out what we conclude about the variances, namely whether they're equal or not, will determine the type of mean test that we ultimately might use. And so there are a couple approaches here. We could test for the equality of variances, and if we do not reject that equality hypothesis, then we can choose what we call a pooled mean test, which is ultimately a t-test that's based on pooling the data altogether. Now, I should note that the test of equal variances depend on whether or not we can assume the data are normal or not, the particular test. There are various tests. Another approach is not testing the equal variances, and just go straight into a mean test that doesn't assume equal variances. You might ask, well, why not do that? Well, it turns out that if we conclude that the variances seem to be equal, then we get a more powerful test. The pooled mean test is more powerful. So there's a trade-off that we're playing with.
Let's go down the route of testing the equality of variances first, sometimes referred to as a test of homogeneity of variances. I noted that the tests that are available depend on the distribution. In particular, one test depends on the underlying distribution for the data to be normally distributed. We can see here the data separated by away versus home, summarized with a normal quantile plot and a histogram. And in both of these cases, we can see that the data are compatible with the normal distribution. How do we test for equal variances? Well, I go to the fit y by x platform, giving free throw attempts per minute as my y and the categorical variable where as my x. I'll get this output, which is just a side-by-side comparisons of the away versus home. Then go to the red arrow option and choose unequal variances. We see reported a number of tests and p-values. The Bartlett and Levine down here are the most commonly used tests when the data are compatible with the normal, and that seems to be the case here. The Brown-Forsyth is a good alternative when you have non-normal situations. I won't discuss the other ones shown here. They're all really suggesting the same thing. If I look at the Bartlett and Levine, the p-values are very large, indicating we cannot reject the null hypothesis of equal variances. Now that we've concluded it's safe to assume equal variances, let's show you the manual calculation of the statistic, the pooled t-test. What we'll need are the means for the separated groups of away and home, the variances, and the sample sizes. I did that through the Analyze Distribution platform, and in the by dialog box, I gave the where variable, and then this allowed me to get all the various statistics that you see before you. Here is the test statistic. It is a t-statistic that is looking very similar to what we learned in the one population mean test. We have an estimate, in this case an estimate for the difference in the population means, which is y bar 1 minus y bar 2, minus the hypothesized value, which is 0. We're saying there's no difference in the null, over the standard error. Now the standard error is given by this formula here that combines the two groups, but using what we call a pooled sample variance that ultimately, as you can see here, is pooling all the data into one. I'm not going to go through the whole algebraic breakdown. It is what you see. And under the null hypothesis, this test statistic follows a t-distribution with n1 plus n2 minus 2 degrees of freedom. That should make sense. The total sample size is n1 plus n2, and there's two parameters we don't know, mu1 and mu2, so we lose those 2 degrees of freedom. You can review this slide, but basically what we're doing is feeding these sample variances and sample sizes to get the pooled variance. As you can see here, the t-test is the difference between the sample means minus 0, which I don't need to show, divided by the square root of the sample variance times this quantity based on the sample sizes. And in the end, we get a t-statistic of minus 0.833. Right away, we have a sense of what this result is. Using a basic back of the envelope rule of thumb of plus or minus 2 as a range where we would expect 95% of the time the t-statistic to fall. If the null is true, this is well within, so we're leading down a path of no rejection. Let's now have JUMP do the calculation. So back to the fit y by x platform, under the red arrow option, I'm going to choose means ANOVA, and the key is to see the word pooled t. And here we see the results. We see a t ratio reported to have the same numeric value that we had computed of 0.833. Now we got minus 0.833. The reason being is that we did away minus home and JUMP did home minus away. This is inconsequential, and you can actually have JUMP do it the other way. But in the end, this is a two-sided test, so it really doesn't matter. It shows us the p-value, and I'm going to look at the absolute value because that's a two-sided test, and we see the p-value to be 0.4074, which is insignificant at the 5% level. Furthermore, it gives us a confidence interval for the mean difference, and notice it ranges from a minus value to a plus value, which includes the possibility that mu home minus mu away equals 0. Again, a confirmation of insignificance in terms of the data results. Now let's show you how to use JUMP to test the mean difference without assuming equal variances, which is the conservative route. That is done by choosing, rather than pooled, the option down here of simply t-test. Here is the output. Notice JUMP is saying assuming unequal variances. Now the t-ratio and the p-value are nearly identical to our earlier output. This is because the variances between the two samples were so close. However, if we have a situation where the variances between the two samples suggesting the variances between the two populations are very different, then we could get dramatically different results between the pool t-test and this test. And this test would be the more appropriate test under that scenario. To conduct the test in Excel, you have to have the data separated, not in one column like in JUMP. So I have here in one column the away data and the other column here the home data. In the toolpack, there is indeed an option for testing under the assumption of equal and unequal variances. Here I'm just showing you the unequal variances. I highlight the columns. I'll dump the output in the Excel spreadsheet. Here's the output, and you can see all the same numbers we had earlier from JUMP, from the means and variances and number of observations, and in terms of the t-test result of minus 0.833, and finally the p-value of 0.4074. So Excel is doing the same thing as JUMP and vice versa. Now, interestingly enough, what we've done earlier with the t-test can actually be done and subsumed within a regression approach. Regression will be the main machinery of this course, so I'm just giving you a preview. I've created a column called home, which is called an indicator variable. You'll learn that later. And I'm going to run a regression of free throw attempts per minute on this indicator variable. And this gives us an equation. Now home will either take the value 0 or 1. Go ahead and stick those values in and you'll see you get the same Y bar values from a previous slide. And I want you to note that in the regression output, it reports a t-ratio, and you see here the t-ratio of 0.83. That's no accident. It's the same value we saw just a couple slides back, and indeed that same p-value of 0.4074. So this is giving you a preview of things to come.
All right, so we've looked at the situation of two populations, home versus away. What about more than two? Let's consider data here from a direct marketer on the amount of sales that customers spend. That they have a database on customers and how much money they spent buying from this direct marketer. We have the ages of the customers, the gender, their salary, and various things like that. We're just going to focus on the amount spent, and we're going to look at age.
In this data set, age is actually grouped into 3 groups: young, middle, and old. So when I do a plot of the amount spent against age, we get box plots for each of the groups. We can see young spends less than middle and old, which makes sense. Now, it would probably be better for presentation to have it in chronological order of young, middle, old. And that's easily done. You can go to the age column, right click on it, go to column properties, and then you'll see value order, and you can arrange it in the order you so wish. Here are the box plots rearranged in order. Now, what we're wanting to do is test whether the mean of young equals the mean of middle equals the mean of old. Again, it depends on what we can assume about the underlying variances. It appears that the variance of the young group is significantly different, in this case smaller, than the variances of the other groups. Standard ANOVA which is the testing of multiple means, assumes equal variances. So we should not use standard ANOVA here. I have two outputs here. I have the histograms of amount spent separated by the age groups. I did this in Graph Builder and then dropped into the grouping zone the age variable that will separate the histograms. We can see here that the data are not compatible with the normal distribution. So in the unequal variance option that gives us this output, we would want to choose the Brown-Forsyth test because that doesn't assume normality. And we can see it's significant. The p-value is very small, indicating we cannot assume equal variances. If you look on the previous slide, at the bottom of the variance test is something called a Welch's test, and here I've snipped it out on this slide. The Welch's test tests the equality of means, but does not assume that the variances or standard deviations are equal. And we can see the result, a p-value that is extremely small, meaning that we have strong evidence to reject the null hypothesis that all the population means are equal. I'll note in Excel, there is no way to test 3 or more means where the variances are not assumed equal. Let me note another approach that we could have used for these data. Namely, we could try to stabilize or make more constant the variance. And we've learned that the natural log transformation can often do that. Here we see the spent data in natural logged units. And now in these units, you can see the variances across the different age groups are much more constant. Now I'm noting this because this use of natural log transformation to stabilize variance will be a common strategy when we get to regression.
Let's turn to a completely different example. I'm sure you've heard of the drug hydroxychloroquine. There was hope, particularly in the beginning of the pandemic, that hydroxychloroquine could be an effective drug to combat COVID. And that hope was bolstered by a July 2020 study that came out of the Henry Ford Health System in Michigan that reported effectiveness, namely lower mortality with its use. So that got things rolling as being a potential game changer and hailed as such by various folks in our society, from politicians to certain media outlets. Let's take a closer look in this to this question of hydroxychloroquine.
To truly believe that a treatment is effective, the study should be based on a randomized experiment. It is also preferred that the experiment be double-blind, meaning that neither the person taking the medication nor the doctors administering the medication know if they're taking, in this case, hydroxychloroquine or a placebo. What about the Henry Ford study? It was not a randomized controlled experiment. It was a retrospective study of past patients for whom doctors selected to get the drug or not. You can see all the built-in biases that are happening here. In fact, a doctor at Cleveland Clinic stated, "I can tell you it doesn't prove anything." Oxford ran a proper study, a randomized experiment. They had two groups that were randomly assigned to, namely there were 1,561, I show here on the bottom, patients that were given hydroxychloroquine, 3,155 that were not. Of those, 418 of the hydroxychloroquine group died. 788 that did not receive hydroxychloroquine did not die. The proportions of 0.268 versus 0.250 And the study reports a p-value comparing these proportions of 0.18, which is not significant at the 5% level, and thus they conclude hydroxychloroquine was not associated with reductions in mortality. We can put the Oxford data results in a jump data table to get the conclusions that they arrived at. I'm going to use actually the HELP followed by sample index calculators hypothesis test for two proportions tool that's in JUMP. I give all the values in terms of how many people in each of the groups, how many died in each group, and you can see in the end that we get the p-value that they reported, 0.18. Given this p-value is greater than, let's say, 0.05, we do not reject the null hypothesis that the two population proportions equal, or another way of saying it, we do not reject the null hypothesis that the difference between the two population proportions equals 0. Hydroxychloroquine has no effect according to this study. Let's turn now our attention to formally questioning the relationship or not between categorical variables. Recall that with categorical variables, we are basically making tally counts of how often a given situation occurs. With two categorical variables, we're actually making tally counts of how often the intersections between category levels occur. Now, the resulting counts can be displayed in a table called a contingency table or a crosstab, and it's very popular in the marketing area because there's a lot of survey type data, which often are categories against categories. The question we want to investigate is if there's any relationship between categorical variables. Here's a simple example. Consider a survey of 1,802 randomly picked online users, and we're going to look at the category of gender against the category of using Facebook or not. Here is a contingency table. We have cells that are intersections. For example, the 525 are the number of users who are male and uses Facebook. We can add across a given row to get row totals. So this would be the total number of users that use Facebook. We can add down the column. Here, adding down the male column, we find 846 users are male. And if you add up all the cells inside the contingency table, or add down the row margins, or add across the column margins, all will arrive to the same total of 1,802. A contingency table, or sometimes called a two-way classification table, has us focus on a fundamental question of whether or not the main categorical variables are independent of each other or not. In this case, we are talking about asking if Facebook usage is independent or not with gender. With a contingency table, we can estimate various probabilities. For example, we can estimate what is the probability an individual is male. It's randomly selected from this group, and we find that probability to be 846 out of the 1,802, which is 0.469. But here's a more interesting question ultimately. What is the probability the individual is male given we know the individual is a Facebook user? That would be taking the 525 out of the 1,204, which would be 0.436. And what's the probability an individual is female given the individual is a Facebook user? And that would turn out to be 0.564. So there seems to be a greater chance that an individual is female in the Facebook population. From a business perspective, this can suggest the type of advertising that might be directed to the Facebook platform. Let me note one basic probability result. we have to start with the idea of what independence means. If we have two events A and B being independent, it means that the probability of A occurring given B has occurred is equal to the probability of A. That means the occurrence of B or also the non-occurrence of B, it doesn't matter, doesn't impact the likelihood of A occurring. Given this definition, we can show that in the special case of independence, the probability of A and B occurring equals to the probability of A times the probability of B. We will leverage on that fact. Here is a general contingency table. We have here a number of columns, and I'll generically call that C columns, and we have a number of rows, and we have in general R rows. The intersection between any given row and column is the observed count. So for example, row 1 intersecting with column 1, we observe 1, 1. The subscripting indicates row and then column. If we were to add across a row, for example, row I, we add all these observed counts, we would get RI, the row count, the row margin. If we were to add down some column, let's say column J, all the counts, we would get a column count or a column margin, in this case CJ. And if we were to add everything up, whether all the O's or add down the row margins or add across on the column margins, however you want to add them up, you'll have the total sample size N. Given the notation on the previous slide, what is the probability that we have an observation coming from row I? Well, that would simply be Ri divided by N. That's this ratio right here. What is the probability an observation comes from column J? Well, that would be Cj divided by N. But let me now ask the next question. What's the probability that an observation falls in that cell, which is the intersection of row I and column J? That would be the probability of row I and column J. And if we can assume independence, then that probability is the multiplication of those two events, as we showed 2 slides back. That would be Ri divided by N times Cj divided by N. The next question would be, given that probability, then how many observations do we expect to fall in that cell if the categories are indeed independent? Well, that's simple. All we have to do is multiply N times that probability above, assuming independence. So it's N times Ri over N times Cj over N. One of the N's cancel. So the expected number of observations falling in row I, column J, if the categories are independent, equals Ri times Cj divided by N. Let's introduce you to the actual test. The null hypothesis is one of independence, no association. If the null is true, then we know the expected counts that fall into each of these cells. That's from the previous slide. Put that against the actual data, the observed counts. If the null hypothesis is true, then we would expect the observed and the expected counts to be close. If the null hypothesis is not true, then these counts will differ significantly. Now we want to compare across all the cells. And how do we do that? Well, we do that with this following formula. We take the observed count in any given cell minus the expected count, and we square it. The reason we square it is because we don't want to have the pluses in some cells cancel out the negatives in the other cell, and then we sort of lose out on the picture of what's going on. We divide by the expected count because we want to have that difference relative to the magnitude of the expected count. Imagine comparing 101 versus 100 versus 1001 versus 1000. They both differ by 1, but clearly the difference is less in terms of like a percentage idea for the 1001 versus 1000. So we divide by the expected count. And then we have just two summation signs here. Remember, summation sign means simply add them all up. I'm having two summation signs because we're adding across columns and across rows. Don't be too concerned about this detailed notation. It just simply means add them all up. And when we add them all up, we get a statistic that's called a chi-squared statistic. If the null hypothesis is true, then the chi-square statistic follows the chi-square distribution with the degrees of freedom equaling r minus 1 times c minus 1. If you're curious to know why the degrees of freedom is r minus 1 times c minus 1, let me give you a simple explanation. Remember, degrees of freedom is indicating the observations that can be free to be whatever they may be. They are not restricted. For example, let's look at row 1. Given we have R1, let's say it equals 105. And if we were to add across the first C minus 1 cells, and let's say that adds up to 100, that would imply that this cell has to be 5. It's restricted. It has no choice given the row count has to be 105. So if we look row by row, all these cells here in column C are restricted. We can go through the similar argument going across the column counts, noting that given a column count, the first r minus 1 rows can be free to be whatever, but the rth row is restricted given the column count. And then finally, I just have here the overlap. Whether you want to look at it from the row perspective or the column perspective, this is restricted. The only cells that are unrestricted are in green here, and there's r minus 1 rows and c minus 1 columns, so the number of unrestricted cells is r minus 1 times c minus 1. Let's return to our example. Here's the contingency table with the row margins and the column margins and the cell counts. Let's look at one of the cells. We see here that the observed count in row 1, column 1, which is using Facebook and being male, is 525. If Facebook usage and gender are independent, then we have an expected count of 1204 times 846 divided by 1802, which is 565.252. We can similarly get the other expected counts in the other three cells. Indeed, here are the observed and expected values for each of the 4 cells. It's a good idea to confirm the values yourself. We're going to compare these values in one statistic called the chi-square statistic. Here we find the calculation of the test statistic. We take the observed minus the expected, divide by the expected, and do it for each of the 4 cells and add them all up, and we get 16.281. This statistic under the null hypothesis would follow a chi-square distribution with 2 minus 1 times 2 minus 1, which equals 1 degree of freedom because the number of rows equals 2 and the number of columns equals 2. We can now find the p-value, which is the area more extreme than what we have observed. Using the distribution calculator, I choose chi-square, give 1 degree of freedom, input the 16.281, look to the right, that would be more extreme. The p-value jump reports is indeed less than 0.001. If I go to Excel, I can use the chi-square distribution right tail function, again giving 16.281 1 degree of freedom, and Excel reports how small that value is, 0.000054688. Essentially, this is a p-value near zero, and it's suggesting with strong evidence that the null hypothesis of independence should be rejected. Here's how you get JMP to do the chi-square test based on the data. You would put in the data table the combinations of all the cell intersections. So I have a column called use Facebook, yes and no, gender, male and female, and I gave the counts. Then we go to the fit Y by X platform, giving use Facebook as the Y. We could do it the other way, but I'm going to put use Facebook as the Y and gender as the X. And then we're going to put the counts in the frequency dialog box. Here's what we get. We get the mosaic plot, which is a visualization of category against category. We get a contingency table. Now you can play with what you want reported in each of the cells through the option pull down. I just am asking JMP to give me observed and expected counts. We get the test results. There's a couple chi-square test results here. We're going to look at the one called Pearson. That indeed is the 16.281 value we computed and the associated very small p-value. So we have strong evidence to reject the null hypothesis of Facebook usage and gender being independent. There is no convenient way to do this test of independence in Excel. Let's revisit the hydroxychloroquine example that we used to test the equality of two proportions. We can actually look at this problem from the perspective of a contingency table. The two categorical variables are outcome, die, versus survived, the treatment, getting the drug versus not, and we have the counts. We can feed these columns into the fit Y by X platform and get our contingency table results. We see the mosaic plot, we see the contingency table, and indeed we see in the end the same p-value of 0.18. Given it is large, we cannot reject the null hypothesis of independence between outcome and treatment, i.e. there is no effect of the drug on the outcome. They're unrelated. In the previous examples, we had the summarized counts by cell. However, in some data sets, we may have the original raw data and we need to have the software do the counts for us. Consider the classic application of the Titanic survival versus the class that is associated with the individuals on the Titanic. So we have under class, we have first class, second class. We also have being a crew member. We have the age, the sex, and we have a column whether they survived or did not. Here we have for the Titanic, the class breakdown, crew, first class, second class, third class, and we have reported the percentages of individuals that fall into each one of these classes. We have separately the category of survived, yes versus no, and we have the percentages. We see here, for example, 68% did not survive and 32% did survive. Now these are in separate silos. They don't tell us the information about the breakdowns of survival or not by class. So we can look at a mosaic plot of one variable against the other, and this gives us a clearer picture. We can see, for example, for first class, there is a higher percentage of survival than second class, but second class is higher than crew and third class. third class and crew seem to be about the same survival rate. Now I went to the Fit Y by X platform, but I'm not going to give some predetermined counts in the frequency dialog box. We'll just go ahead and give the one variable against the other variable to get the following contingency table, and you can see the breakdown again of observed versus expected. The punchline is at the bottom here with the p-value. The p-value for the chi-square test is very small. Thus, we would reject the null hypothesis that class and survival rate is independent. They are not. Earlier in this lecture, I noted that when looking at categorical as a y variable against a categorical or a non-categorical, we can use a logistic regression model. This will not be covered until the very end of the semester, but I want to give you a preview. Here we're going to look at predicting survival rate based on predictor variables that are the class that an individual is in. So I created these predictor variables of crew, first class, second class, third class, which are 0, 1, 0 being no, 1 being yes. And I'm going to feed this into the logistic regression. Now, because all you need is 3 to determine the fourth, I only have 3 indicator variables, that's the 0, 1 variables in this logistic regression. And what we get out of this, based on taking all this information here under estimates and feeding it into a formula, which you will learn later, we can come up with a formula for predicting the survival rate depending on whether an individual is in first, second, third, or crew. Crew would be when the individual is not first, not second, and not third. And here is the formula. It's a different take on how to come up with the ultimate conclusions and analysis of the data. What's nice about logistic regression is that we can add other variables here that are not categorical to give us the prediction of survival. For example, age could be added to this logistic regression, which you cannot do in the contingency table approach. We see here the logistic regression gives us the same chi-square result and p-value. So in a sense, the logistic regression subsumes the contingency table and is a more general approach for modeling data. I now want to cover the concept of correlation, which is related to looking at a numeric variable against a numeric variable. It's a springboard into regression. Consider this data on NFL teams in 2019. This is American football teams. And we're seeing that we have information on the winning percentage for that season against a whole bunch of statistics team by team. And there's 32 observations. First thing we could do is get a visual impression. I'm going to look at, for example, winning percentage against the number of yards passed in that season. And what do we get from this visual impression? It doesn't seem like winning is associated with passing yards. The question now is, how can we summarize this plot into a numeric measure? Before I give you the formula for the numeric measure, namely the formula for correlation, let me reintroduce you to standardizing. Now, we did this when we looked at the normal quantile plot. I'm going to standardize both the X data and the Y data, and we do that by taking each observation, subtracting off the mean of the observations, and then dividing by the standard deviation. When you rescale the data by standardizing, you have it in a scale of how many standard deviations away the observation is from the mean. Negative observations are below the mean, positive observations are above the mean, And in general, it can be shown that the average of the standardized value, the sample mean of the standardized variable, is 0, and the sample standard deviation is 1. Why do we standardize? Well, let's consider the following situation. Suppose I have a variable x1 that has the values 16, 4, and 10. The sample mean would be 10. The sample standard deviation would be 6. If I standardize by taking each observation minus the mean dividing by the standard deviation, I get standardized values of 1, -1, and 0. Now let's say I change the units on x1 by multiplying all the observations by 10. Well, obviously the mean and the standard deviation will inflate based on that multiplying times 10. But notice the standardized values do not change. Suppose we divide by 10. Same thing. The standardized values are unaffected. Suppose I add the number 5 to all the observations. Same thing. The standardized values are unaffected. So standardized values are unaffected by unit changes. We're now ready to see the formula for correlation. We take the cross products observation by observation between the standardized x value and the standardized y value, add up these cross products, and then divide by n-1, which is essentially dividing by n. So we're basically having the average cross product of the standardized x and y values. Now this is maybe a bit messy looking. Another way to write it is the sum of the cross products and then just put the fraction 1 over n-1 in front of that sum. Let's get intuition of the correlation through a visualization. Here I have the winning percentage against yards passed. What I then did was I added reference lines at X bar, the average yards passed, and a reference line at Y bar, the average winning percentage. We remember that we're taking a cross product of x minus x bar divided by the standard div against y minus y bar divided by the standard div. Let's consider each of these quantities in each of these 4 quadrants. In this quadrant here, which I call plus plus, x is greater than x bar and y is greater than y bar for each of the points. So we'll call that plus plus. Here in this quadrant called minus plus, the x values for the points are less than x bar. Thus we get an x minus x bar being minus, and the y values are greater than y bar. Thus we get a plus deviation. Here all the deviations are for x negative and for y negative because they are both less than their respective averages. And then we have the plus minus region. When we multiply a plus times plus, we get a plus. When we multiply a minus times a plus, we get a minus. A minus times a minus, we get a plus. A plus times a minus, we get a minus. We're adding up all these contributions based on multiplying the pluses and the minuses. And if we have a scatter that is basically showing no relationship, so there's a sort of equal dispersion of observations in each of these quadrants, then basically the pluses, which are from this quadrant and this quadrant, will cancel out the contributions from the minuses, which comes from these 2 quadrants, and thus the correlation in the end will be near 0. I've already talked you through this notion here that indeed this kind of scattering with points that are falling in each of these quadrants here will just all sort of cancel each other out pretty much and give us a correlation near 0. However, if we look at win percentage against yards rushed, we get a bit of a different picture. Now there is one point out here that's sort of skewing things a bit, but for the most part we see a tendency of a positive relationship in the scatter plot. There's more going on in this quadrant here and this diagonal quadrant here. to dominate out the quadrants on this diagonal, leading us to have a correlation that should be more pushed in the positive direction. Here we have winning percentage against the percentage of interceptions thrown by the quarterback of that team. And we see here a negative tendency. We have more points that are falling in these quadrants, the minus plus up here and the plus minus down here, to dominate this quadrant, leading to a correlation that should be more negative. Here's a figure from a textbook that I actually wrote that's giving you a sense of scatter plots to correlation. Here we have the correlation of 0 because there's really nothing going on between the two variables. Now we have a bit of a negative relationship, and thus a correlation, as you can see here, is minus 0.3. But down here, the correlation is stronger and negative as the magnitude gets larger. For this one, it's minus 0.7, and this one, it's minus 0.99. Here we have a couple positive scatter plots, and again, the larger magnitude the correlation is, the more clear the pattern is in terms of the strength of the relationship. What would be the correlation between these two variables? Clearly, they are very related. They're super related. But what's the correlation? The correlation actually is 0. Why is that? Give it some thought. Remember our crossbars? Here, the observations in this quadrant will cancel out the observations in this quadrant, and these two will cancel each other out. The implication is that correlation is a measure of linear association, not a measure of just is there a relationship or not. Let me summarize. Correlation is unaffected by unit changes. That's because it's based on standardized values. As a unitless measure, it always falls between -1 and +1. The closer it is to +1, the stronger the positive relationship. The closer it is to -1, the stronger the negative relationship. Correlation is a measure of, do we see the possibility of a line for the data? Correlation doesn't tell us what the best line may be. That is the upcoming topic of regression. There are many ways to get the correlation value in JUMP. One way is to go to analyze fit y by x, give the y variable, in this case winning percentage, and the x variable being yards passed. Then under the red arrow option, you'll see summary statistics, and we'll get means and standard deviations reported, but we'll also, as I boxed off here, get a correlation reported. So the correlation in this case between winning percentage and yards passed is 0.118355. Another place to get correlations is under Analyze Multivariate Methods, Multivariate. When you get to the multivariate dialog box, you can actually give it more than two variables. I'm giving winning percentage, yards passed, yards rushed, and the interception percentage, and it gives me all the pairwise combinations. You see, for example, win versus pass yards is that correlation we got on the previous slide of 0.1184, but you see all the other combos of correlations. The fact that there's ones down the diagonal is because the correlation of any variable with itself is 1. And what's above the diagonal is symmetric with what's below the diagonal. So you don't really need both sides of the diagonal, but it's all correct. JUMP also can give you nice visualizations, like here a color map of the correlations. The darker is closer to the darker red is closer to 1, the darker blue is closer to -1. So it's kind of like a heat map of sorts on correlations. In Excel, there is a function that you can put into the spreadsheet that is the correlation calculation, or you can go to the tool pack and find the correlation option. Now I've highlighted more than one column as I just did in JUMP with the multivariate option, and let's see what we get.
And we get what JUMP gave us in that multivariate section. The ones down the diagonal, just correlation with itself, and there's those same correlations that we saw earlier. It's only giving the lower triangle of the table where JUMP gives both. Doesn't matter either way.
In the output showing the correlation between win percentage and yards passed, we found a correlation of 0.1184. That's not zero per se, but that's not the way to think about it. We have to ask the question, is that correlation reported significantly different than zero? That's an inference question. We want to test the hypothesis that the underlying population correlation is zero versus not. We can conduct the test by looking at the output reported to the right of the correlation value. We see a p-value here of 0.5188. Since that's large, we cannot reject the null hypothesis that the underlying correlation is zero. In a similar way, we can look at the confidence interval, which ranges from minus to plus. This is a confidence interval on the population correlation, and the value of zero is in here, so we cannot reject the possibility that the population correlation equals zero. Let's end on the age-old warning correlation doesn't imply causation. You can look at this cartoon to understand the implication of that warning. It was Sir Ronald Fisher, the father of modern-day statistics, that stated the calculation of correlation coefficients, total or partial, will not advance us a step toward evaluating the importance of the causes at work. It turns out that not all practitioners care about this warning, and they will sweep it under the rug. Consider the examples I gave in the beginning of the semester. Target is exploiting relationships in the data to predict whether a couple will have a baby or not. Walmart exploited relationships in the data to realize that there's a greater interest in having Pop-Tarts when a hurricane is coming. In either case, the organizations were not concerned about the why. They're not concerned about what factors explain the behavior, and they just exploit the what, the correlation. Of course, not all applications will ignore the why. In medicine, we have to have a firm belief based on the data analysis that a treatment causes improvement of a patient's well-being. Here we have a manufacturing setting where a manufacturer is looking at data, but ultimately they want to determine, based on the relationships they found, the why, the root causes. So in the end, whether it's purely for prediction purposes or using the data to move us in the direction of getting at the why, this all depends on the context of the problem. Determining causation beyond correlation is a non-trivial task. How do we know beyond X and Y being related that X causes Y? One way is to design an experiment, a randomized experiment. That's the ideal way of doing things. And we alluded to that already with the hydroxychloroquine story. Other considerations that you might take at hand is your thought processes to, let's say, eliminate common variables. Consider the case where we look at data on the number of drownings in a large city versus the ice cream consumption in the large city. If you were to look at these variables, you'll find they're strongly correlated or related. This could lead one to the wrong conclusion that ice cream consumption causes drowning. However, we realize there's a common variable to each of these variables, weather.
When it's hot, people swim more, and thus there's more drowning. When it is hot, people eat more ice cream. Thus, we see the relationship between the two variables evolving. On the other end, when it's cold, people swim less, there's less drowning. When it's cold, there's less ice cream consumptions. So there's no causality of ice cream causing drowning. They're actually at the end of puppet strings of weather. Can we eliminate all these common variables that might be out there to ultimately determine with confidence that we really have a causation between the variables of interest? That's a difficult task because there's not only variables that are obvious, but there could be an infinite number of variables we don't even know about. Here's another thought process. If you want to talk about X causing Y, you need to demonstrate that it is unreasonable for Y to cause X. Suppose we're looking at the relationship between advertising and sales, and we find a positive relationship. Our inclination is to thus believe and want to believe, and that's why we do advertising, is that advertising causes sales. However, what if we think about it this way? When sales is going well, we have more money, and with more money, we can dump it into advertising. When sales is not going so well, we have tighter budgets and we cut back on the advertising budget. So maybe it's sales causing advertising, not the other way around. Now, obviously, the argument is more strong toward advertising creating sales based on marketing research results and all that. But I just want to give you this thought process of, could it be the other direction? And if it's the other direction, that really throws us for a loop on believing that X causes Y, because maybe it's Y causing X. You have to go through all those thought processes to ultimately build your confidence on causation if you don't have a designed experiment. On the previous slide, I gave you some thought processes about coming to the conclusion of the possibility of causality. In general, doing randomized experiments is often not feasible, so there are folks that have provided criteria, checklists to come to hopefully a conclusion of causality based on, again, some sort of thought processing. Bradford and Hill provided a criteria for observational data, that is, data that is not the result of a randomized experiment, in the public health area. I'm not going to read through all of them. They have been tailored for other applications, including business applications. We have here a checklist. The first one is the obvious: strength. We need an association before we can even talk about causation, and the stronger the association, the less likely it is due to chance, and then we can talk about possibly causation. Consistency, that's an important one. Is the association observed in multiple studies across multiple populations, places, times, and by different researchers? Let's look at the fourth one, a timing. Is the effect temporally subsequent to the cause? If we have something causing, we must have a response thereafter. So the variable must come first, that's causing, and the response will come thereafter. Do we see that? A gradient. Do we see that the incident of, let's say in this case, a disease is consistently getting greater when you increase, and as they note here, let's say cigarette smoking? Plausibility. Is there some scientific theory that suggests indeed why there should be causality? And that's the next one, also coherence. Does it make sense given the science? Now, Bradford and Hill does mention an experiment. That's ideal, but we really have to rely on these other criteria. Another situation that gives us strength toward causality, and it was listed as one of the criterion on the previous slide, that one related to timing, is namely what I'll call interrupted time series, or sometimes called intervention analysis. If we have a time series on some variable of interest, and we know that there was a certain intervention and no other interventions that we're aware of occurring at a certain time, and the time series has fundamentally changed, that gives us strength toward a causality argument. Here are actual data on coronary events in Italy with a before and after of an implementation of a smoking ban in public places. We can see a clear interruption in the time series, that the intervention has clearly given us a change in the time series. And this would be an argument towards the causality of that public policy decision. Here's one last consideration. Again, it's this idea of time effect, something happening before and then the result happening down the road. It's called Granger causality, named after Clive Granger, who is a Nobel Prize winner in economics. He developed his causality arguments in economics, like interest rates changing and then a certain amount of time down the road, inflation changing. But it can be applied to many applications, the relationship between CO2 emissions and climate. The idea is that there's this lag effect, and we can model it in a regression type setting. As you can see here, we're presuming that in the end, X is causing Y. So when X upticks a certain number of periods down the road, and consistently a certain number of periods down the road, the Y will uptick. And also when it goes down, the Y will go down. As you can see here, again, uptick in the X, the uptick in the Y. So that's another argument. There's a lot of commonality in these criteria, but these are all important thought processes that you have to go through to convince yourself that you can talk causality. Okay, we've given you a lot of stuff here with this lecture. We're ready to keep on getting closer and closer to learning how to build regression models and other types of models. Have a great one. Talk to you soon.